please.
Thanks. Maybe here?
Yeah, okay, thank you.
5 minutes, I will show you that it's 5 minutes. Okay.
Sorry?
5 minutes later, I will give you a signal for 5 minutes.
Okay.
All right, our next speaker is Qiyuan, who's going to talk about mechanized reasoning about array-based trees in separation logic. Please.
Okay. Hello, everyone. My name is Qiyuan, and I'm currently a PhD student from National University of Singapore. And I'm greatly honored to be here on behalf of the authors team to present our work. So as the title suggests, our paper is about array-based trees, that is, tree data structures implemented using arrays. So let me start by introducing what's interesting about them. So one typical way to implement a tree data structure in an imperative programming language like C is to use pointers. And pointers are used to connect adjacent nodes. So for example, for a binary tree, a node may store pointers to its parent and its two children. For a generic tree, which is a tree with unbounded number of children, nodes can be connected vertically by having pointers to the parent and to the first child, and children nodes can be connected horizontally by having pointers to the right sibling. Alternatively, in some special cases where nodes are uniquely labeled by different integers, it might be feasible to implement array-based trees where a tree is stored into one or more arrays. For example, in C, we can use a struct array to store a tree such that each element of the array contains the information of some node. And consequently, we can use array indices instead of pointers to refer to nodes. Moreover, we can use a dedicated integer like -1, which will never be a valid node index, to represent the null pointer. And sometimes array-based trees are preferable to the more conventional pointer-based ones. There can be different reasons to prefer array-based trees, and one of them is that array-based trees may enjoy time or space efficiency. For example, it takes only constant time to access the information of some node on an array-based tree, because array access takes only constant time. But for pointer-based ones, the access may require a linear time tree traversal. However, while there is much work about verifying programs that operate with pointer-based trees, formally reasoning about array-based trees can pose some new challenges. Now let me illustrate in more detail the challenges that we are tackling in this paper. We consider reasoning about array-based trees in separation logic. So in order to do that, we need to first formalize them in the language of the logic. More precisely, we need a representation predicate for array-based trees. To this end, we can utilize the representation predicate for arrays. We first assert that there is an array with base pointer p, and then describe the content of the array according to the logical tree with a pure proposition. So this pure proposition can be defined recursively on the logical tree. And we also assume that each node of the logical tree carries some unique index. As a concrete example here, consider the situation where this tree TR is stored in the array L. Then the pure proposition will be a conjunction of equalities where each equality captures some information of a node. For the node 3, for example, the equality tells that in the third element of the array L, the parent field should be 0, the right sibling field should be -1, and the first child field should be 4. Although the representation predicate defined in the last slide is useful in some cases, it cannot facilitate the reasoning about programs that change the structure of the tree, and we refer to those programs as the structure changing operations. One example is this move first child function, which moves the first child of some node SRC to be the first child of some other node DST. This is easy to implement, so I omitted the concrete code. But one noteworthy thing here is that the modification of the tree structure is reflected on the content of the array. So the program is realized by modifying the fields of some specific elements of the array. One example is that for the tree on the left-hand side, if we execute move first child 3.0, then the tree will become the right-hand side one. And now the problem comes, how to properly specify and verify this program. Basically, there are two important requirements to fulfill. First of all, it's necessary to specify what parts of the array have changed and how they change. In the example below, there are only 3 elements of the array getting changed. They correspond to node 0, node 3, and node 4. Moreover, we need to prove that the other nodes, which are not touched by this program, are unchanged. And put the two requirements together, what we want is something like the frame rule in separation logic, which allows us to do localized reasoning on changed parts only, so that we don't need to additionally prove that the other parts are not changed. However, localized reasoning requires separating the array into different parts, while a separated part like a subtree may not fit into the representation predicate that we have so far. So in this case, just having one representation predicate for array-based trees is too limited. Another challenge is about certifying tree traversals with assisting stacks or non-recursive traversals. So tree traversals like pre-order traversal or post-order traversal can be easily implemented as recursive functions like this. However, non-recursive traversals avoid overhead introduced by recursion, such as stack frame allocation. Therefore, non-recursive traversals can be useful in scenarios where time efficiency is very important. A basic template for a non-recursive pre-order traversal is like this. The main part is a while loop, and in each iteration of the while loop, the stack top node will be popped from the stack if the stack is not empty. And after executing some code about the stack top node, the children of the stack top node will be pushed into the stack, and then the next iteration will start. Now let me demonstrate how non-recursive traversal works for this example tree. Initially, the stack only contains the root node 0, and in the first iteration, node 0 will be visited, and its children, node 1, node 2, and node 3 will be pushed into the stack. Here, one thing we assume is that the children nodes are pushed into the stack in order from left to right, so the rightmost child of node 0, namely node 3, will become the new top of the stack. And in the second iteration, the current stack top node 3 will be popped, visited, and finally, its children node 4 and node 5 will be pushed into the stack. The rest part of the traversal will be just continuing this while loop. And when the while loop terminates, the whole tree will have been traversed. So if we are going to verify a program that contains non-recursive traversal like in the last slide, we will have to find a loop invariant for some loop like the one here. And the problem is, how can we specify such a loop invariant? This problem can be reduced to several requirements. The first is that the loop invariant should capture the content of the stack. And also, the loop invariant should describe the visited part of the tree. And in some scenarios, the loop invariant should be able to describe exactly what that part looks like. Another requirement is that the stack and the visited part should be consistent in the loop invariant. For example, a visited node should never appear in the stack. Moreover, we need lemmas to establish the loop invariant at the end of each iteration so that we can guarantee that the stack and the visited part are maintained synchronously. And it turns out that finding a loop invariant that satisfies all these requirements is not a trivial task. So far, I have introduced the two challenges of reasoning about array-based tree in separation logic. And in the next part, I will be introducing the strategies for addressing the two challenges respectively. So for the first challenge, recall that it is about specifying and verifying structure changing operations of array-based trees. Our proposed strategy to this challenge is the usage of the dual views. The word dual comes from the fact that apart from the existing array view representation predicate that we have defined, we also develop an alternative tree view representation predicate for array-based trees. each of the two views has its own strength. For example, the array view predicate is specialized in dealing with random access operations, especially read-only operations on arrays. And on the other hand, the tree view predicate is specialized in verifying structure changing operations. Furthermore, the tree view predicate can be derived from the array view predicate and vice versa. Therefore, due to this mutual derivability, we are able to switch between the two different views during the proof as needed so as to enjoy the best parts of both. The tree view predicate is recursively defined on the tree structure. So as defined earlier, the array view predicate consists of a heap predicate for the array itself and also a pure proposition for describing the content of the array. Here, in contrast, for the tree view predicate, we don't include any pure proposition. Instead, the tree view predicate directly describes each element of the array by using the singleton heap predicate. This can be visually depicted like this. So for each node of the tree, there will be a singleton heap predicate asserting that the corresponding element of the array contains some information of the node. Therefore, for this tree, its tree view predicate is the separating conjunction of 6 components. For node 3, the singleton heap predicate asserts that the third element of the array with address p+3 contains this information. And we can see that the tree view predicate is essentially a large separating conjunction. Fortunately, this nature allows us to perform localized reasoning by using the tree view predicate. For example, if we want to focus on the subtree with node 3 being the root, we can first separate the subtree from the subtree from the other parts, and such separation is feasible because separating conjunction is commutative and associative. And then we can reason about the subtree solely by applying the frame rule without the need to prove that the frame part is not changed. Now I will give an intuitive explanation on the mutual derivability between the two views. Actually, in many separation logic frameworks, the representation predicate of array is in general equivalent to the separating conjunction of some contiguous memory cells. From this perspective, the example array L can be regarded as the separating conjunction of its 6 elements. And in light of this, we can unfold the definitions inside the array view predicate. And further, we can compare the array view predicate with the tree view predicate. We can find that there are some corresponding parts which are mutually derivable. And likewise, for the other parts, they should also be mutually derivable. As a result, the two predicates can be derived from each other, and therefore we can switch between the two views as needed. And as mentioned before, the array view and the tree view are specialized in proving different types of operations. So in the case where different types of operations are interleaving inside a program, we may want to switch between the two views during the proof. For example, consider the case where there is a structure changing operation C inside a series of random access operations. To facilitate reasoning about random access operations, the pre and post conditions of C will be expressed by the array view. And on the other hand, we want to use the tree view to reason about C. To this end, we apply the rule of consequence of separation logic. We switch between the two views before and after C, and we use the tree view to reason about C in the middle. So that's for the strategy for the first challenge. And the strategy for addressing the second challenge, which is about finding loop invariants for non-recursive traversals, it heavily depends on the fact that there is some correspondence between a node and the path from the root to it. It turns out that the content of the stack and the visited part can be both precisely represented as functions of the stack top node. For the visited part, it can be expressed as the right half of tree splitting. Therefore, in order to state the loop invariant precisely, it's sufficient to keep track of the stack top node. And for tree splitting, let me first introduce its definition. In this paper, we consider splitting the tree vertically. Given a node in the tree, we can split the tree vertically into two parts along the path from root to that node. And here, I will give some examples. I will use the shadowed area to indicate the right half of vertical splitting. So if the tree is split by node 3, then the right half will contain node 0 and node 3. And if the tree is split by node 5, the right half will contain these 3 nodes. And if the tree is split by node 2, then the right half will contain these 5 nodes. So here, the right half will include the node itself and also all of its ancestors and the subtrees on their right. Now we take a second look at the while loop in non-recursive traversal. Assume that we are doing non-recursive traversal on the tree, and currently the stack top node is node 4. Then an interesting coincidence is that the post-iteration visited part, which means the visited part after the current iteration, is exactly the right half of vertical split by node 4. Furthermore, the pre-iteration visited part, which means the visited part before the current iteration, can be expressed as the post-iteration one minus the stack top node. And intuitively, it is equal to the right half of vertical split by the right sibling of node 4, namely node 5. So therefore, we can describe the pre- or post-iteration visited part as a function of the stack top node. And one thing I want to mention here is that this intuitive equality is slightly subtle to formalize, actually. So you may check our paper if you want to know how it is defined, actually. And similarly, for the stack content, it is also a function of the stack top node. The stack before an iteration contains all nodes on the left-hand side of the ancestors of the stack top node. For example, if the node 5 is at top, then the stack will contain node 1, node 2, and node 4 in order. And the stack after an iteration can be easily derived by popping out the stack top and pushing its children. So to summarize, combining the results in the last 2 slides, it's sufficient to define loop invariants of non-recursive traversals by keeping track of the stack top node. Now that we have developed strategies for the challenges, it will be good to try them out on some concrete case study. And interesting enough, there do exist an array-based tree data structure that involves both structure changing operations and the non-recursive traversal. That is the tree clock. So tree clock is initially introduced in this paper titled A Tree Clock Data Structure for Causal Orderings in Concurrent Executions, which is published in S+PLOS 2022. And as indicated by the title, tree clock is used for recording the causal orderings in a concurrent system, and it's essentially an instance of the logical clocks implemented as generic trees. A logical clock maintains a timestamp, which is a mapping from threads to clock values. And a classic implementation of logical clock is the vector clock. It represents timestamp using an array. And on the other hand, tree clock organizes the timestamp as a tree. The logical clocks can support some clock operations like join or copy. And the good thing about tree clock is that it achieves the optimal asymptotic time complexity in performing clock operations. It achieves better time complexity than the vector clock by taking advantage of its hierarchical tree structure. The tree clock is suitable to be implemented as array-based tree since the number of threads in a concurrent system is usually bounded and the threads are usually having different identifiers. As a logical clock, tree clock supports the join operation, which happens between 2 different tree clocks. Here I will indicate as TC1 and TC2. The join operation is basically a non-recursive traversal over TC2, and during the traversal, there will be structure changing operations performed on TC1 according to the stack top node of the traversal. So the join operation manifests both of the two verification challenges. Therefore, our case study is about verifying the join operation of the tree clock. Tree clock is originally implemented in Java, and we did a faithful translation into C. We defined and verified the functional model of the tree clock in the clock-proof assistant, and the functional model includes the definition of tree clock as an inductive data type, and the join operation implemented as a function of program. We further verified that the imperative join operation in C correctly implements the functional model by using the verified software toolchain, or VST. We used the VST here since we want to have an efficient and realistic and also formally verified implementation of tree clock. In addition to the verification efforts, we also conducted some experimental evaluation to compare the efficiency of array-based tree clocks against pointer-based tree clocks. From the last column, which shows the speed up of using array-based tree clocks, we can see that array-based implementation do bring efficiency. And even better, the array-based tree clock comes with some correctness proof. So in summary, array-based trees is a performance-oriented implementation of tree data structures. In this paper, we identify two challenges, which are also common patterns in the programs that operate with array-based trees. And we propose strategies to reason about those patterns. In this talk, I'm giving some intuitive explanation of the tech of these strategies. And if you would like some more formal explanation, you can check our paper. And if you prefer even more formal explanation, you can check our mechanized development. We have summarized some core parts of our verification efforts into a reusable library. And the QR codes are put on the screen. And that's the end of my talk. Thank you.
Questions?
Thanks for the talk. So another kind of array-based trees, which I think is more compact, is instead of including information about the sibling and the parent and surrounding nodes in the tree node, you could, so for example, for binary trees, you can have in the array the child of that node at index 2n plus 1 or 2i plus 1 and 2i plus 2 or something. So I was wondering if this work could also be applied on such array-based trees.
Yes, I think we can, for those trees, like, I think one example is the binary heap. We can implement a binary heap into an array, and in that case, we can define the representation predicate of the binary heap, like we can define another specific representation predicate for that to represent that array-based tree.
Thank you.
When you're doing the pre-order traversal, I believe it was, maybe post-order, when you're doing the traversal, how much of the fact that it's represented in an array actually is relevant inside that code? Could the same proof essentially work if you didn't have an array representation? And instead of having integers, you would just have pointers?
Yes, I think the strategy here also applies to the pointer-based trees. Yes, one thing I think that the presentation here is based on array-based trees because because typically when we define representation predicate of pointer-based trees in separation logic, we will use extension quantifier to hide the pointers of the children nodes inside the predicate. And therefore, if we use a pointer stack to store the pointers that we are going to traverse, then we may need some additional specification to tell how the pointers in the stack correspond to the nodes on the tree. And I think that that's some additional work which is feasible to do. But here, the presentation might be more easily done on the array-based tree. Yes.
Thank you.
Hello. Can you go into detail about how you achieve constant time random access and how that's different from the pointer-based approach?
Achieve the constant, it's like if we have the index of some node on the tree, then we can just use the array access to access to that node. But if we have the pointer-based tree and we don't have an external like hash map from the node index to the pointers, then we may have to go through the whole tree to find that node. And that may require linear time tree traversal.
Thank you.
Other questions? So maybe I have a question related to the same efficiency thing. You mentioned that traversing the tree is more efficient, but in the case of array-based, especially in your representation, you have to look up the index and do some arithmetic operation on the address of the array, and then look up. So how is it faster than the tree-based approach with the pointers directly given in the structure?
For the, I guess in the traversal, we don't need to do the arithmetic. We can just go through the children nodes by the fields and.
Yeah, but you have to look up the field to see the index, right?
Yes, I guess that will not involve the arithmetic like plussing or something.
Okay. Thank you. Let's thank the speaker again.